Hi everyone, today we're starting chapter 7, which is in the integration chapter. So these notes are about 701. I'll also scan this page and put it on Canvas. So today we're talking about approximating the area under a curve. So what you can see in this diagram, we've got our curve. And what I've done is I've drawn these rectangles. I've gone up to A and across by 1 unit. I've gone up to this point and across by 1 unit. That distance across that 1 unit, we use dx, meaning like the change in x basically. So our dx in this case is equal to 1. Over here, I've drawn the rectangles above the curve. So I've gone up here and across, and up here and across. So I could use the rectangles in this diagram, or I could use the rectangles in this diagram to estimate the area of the curve. And as we can see, the actual area would be somewhere in between the two. I've written some notes on that there if you would like to put that into your books. So you can see in diagram 1, the actual area, the height here is f of a multiplied by d of x. And for this one, it's f of a plus b on 2, so the average of a and b, this point in the middle, the height there, times by d and x. That would give you that area. In diagram 2, we start with the height of a plus b on 2, multiplied by our dx. And for this one, the height of b multiplied by our dx. So these are two formulas we could use to find the area under the curve. If we were to use smaller rectangles, however, the area is going to be more accurately estimated. So what we can see here is I've found the area under the curve by using lots of rectangles. I could cut those rectangles in half, and that would give me a more accurate expression for it. So these are the original rectangles. If I cut them in half, that would just become closer. So the actual area under the curve can be found extremely accurately, in fact 100% accurately, if we take the limit as dx approaches 0. So as the width of this rectangle approaches 0, multiplied by the height of the rectangle would give you the actual area under the curve. So here it is here, the area is the limit as, now I've used a delta x here rather than just dx, just to, that just means a small change in x. So as those changes in x approach 0, this symbol is capital sigma, that means add up, it means the sum of. So the sum of the f of x's multiplied by the dx. Another way we write that in calculus is to use this integral symbol that I've shown you before. So it's the integral of f of x, and we say with respect to x. It's the x's that are getting smaller. Sorry, that one should be delta x there. So that's called an indefinite integral. If we want to find a specific area from, say, x equals a to x equals b, then we can write our integral like this, where we have the end points a and b. We could also use other shapes to estimate our areas.